I want to explain a little bit more about why most total peripheral resistance is found within the arterioles. And in order to do that, I need to give you an equation called Pazos Equation. And Pazos Equation relates to the resistance of a simple cylindrical tube, like a blood vessel, let's say. And fluid is moving through this tube, and it has to be laminar flow, which is normally the case in the body. There's no turbulence here. Now, under these circumstances, we can calculate the resistance of our blood vessel. Resistance is equal to 8L eta divided by pi r to the 4. L is the length of the blood vessel. The Greek symbol eta refers to the viscosity of the fluid that's moving through. So something like golden syrup would have a very high viscosity. You can think of it as stickiness. Blood has a relatively high viscosity as well compared to water. Then r in the denominator is radius. And you can see that the radius of the blood vessel is raised to the power 4. Now what this means is that the resistance of a blood vessel is particularly sensitive to radius because of that power to the 4 factor. So if you have a very narrow vessel with a small radius, that's going to give that vessel a high resistance. Conversely, if you have a wide vessel with a large radius, the resistance is going to be very low. So the radius of the blood vessel has the biggest effect. Well, if you're looking for where the resistance would be in the circulation, you might then think, where is the radius of the blood vessels smallest? And you would conclude capillaries, because a capillary has the smallest radius, and so according to Poiseuille's law, a capillary should have a higher resistance than any other blood vessel for a given length. Unfortunately, things are not quite as simple as that, because in order to work out the collective resistance of all of the capillaries, you would have to think not just about the resistance of just one capillary, but you'd have to think about how many capillaries there are in parallel. Because if you've got lots and lots of capillaries, collectively their resistance will be lower. You can think of this, I suppose, as thinking about the roads that are running into a town. Now, a motorway runs into the town, and that has a wide radius. It's low resistance, which means that it's very easy for the cars to get down it. If you think about a B road is very narrow. It has a high resistance, and therefore it's difficult for the cars to get down it. And of course, if the choice was a motorway or just a single B road, the B road would get very congested, and it would be much easier to take the motorway. The motorway would have a lower resistance than the B road. That's like saying an artery has a lower resistance than a capillary. Of course, that's the case. But if you imagine that there are 1,000 B roads going into the city, the collective resistance of the B roads is reduced. And it's actually quite easy for the cars to get into the city on the B roads now because there are lots of them in parallel. The resistance of an individual capillary is high, but because you've got many, many thousands of them, their collective resistance is low. So if we want to think about where the resistance is in the circulation, we need to think about how wide an individual vessel is, what its radius is, because that's very important. But we also need to think about how many there are in parallel. Now it turns out that capillaries are the very narrowest, so they have the largest individual resistance, but there are so many in parallel that their collective resistance isn't that high. And it turns out that it's the arterioles which have the highest resistance collectively in the circulation. And the reason is because they are quite small, so their individual resistance is relatively high, and although there are quite a lot of them in parallel, there aren't as many as there are capillaries. And if you put those two factors together, arterioles have the greatest resistance collectively. Because they have the greatest resistance in the circulation, and because they have smooth muscle in their walls which allows their radius to change, this is why so much of the control of the circulation relates specifically to the arterioles. That's why the arterioles are so important. Now that consideration was quite theoretical, because it's going to be very difficult to know how many of these blood vessels are in parallel, and of course they're all in different lengths, they're all around the body in different areas. In fact, it would be impossible to use a piece of paper and a pen and to calculate that the arterioles had the highest resistance. Fortunately, there's an easier way of doing it. And what you can do is you can look at how the pressure drops as you move around the circulation from the aorta back to the heart in the right atrium. It turns out that you get a bigger pressure drop across a larger resistor. And thinking back to GCSE physics and thinking about electrical resistors, you might recollect that it's a similar thing with electrical resistors in a circuit. In a circuit, you get the biggest drop in potential difference across the biggest resistor. And similarly, in this case, you get the biggest drop in pressure in the circulation across the biggest resistance. So as you move around the circulation, you move from the arteries to the arterioles, to the capillaries, to the venules, to the veins and back to the heart, the pressure doesn't drop in a nice linear way all the way down the circulation. In fact, you get most of the pressure drop occurring across the arterioles, which you can see quite clearly in a graph such as this. And that large pressure drop across the arterioles tells you that they have the highest resistance. And the reason is, as I've explained, individually they're relatively small and there aren't so many of them in parallel. So the biggest resistance in the arterioles, the biggest pressure drop across them, and that makes the arterioles the key point for the control of the circulation.